Okay, so I'm going to prove for you the Jordan Canonical Form theorem. And so let's start by writing down the theorem. Suppose suppose V is a finite dimensional vector space over F, and say T is a linear transformation of V. If the characteristic polynomial of T splits as a product of linear factors over F, so all the eigenvalues are there and there are no extra irreducible factors, just the linear ones, then you can write down the matrix of T with some ordered basis in Jordan canonical form. And so basically this as a corollary implies that if you have complex numbers as F, then since every linear transformation over a finite dimensional vector space has all its eigenvalues, it always splits like this. Therefore, every complex square matrix can be written or is conjugate to 1 in Jordan canonical form. Right? Okay. So that's that. And now we were proving this. We ended the lecture 23 by writing this down and saying that the proof is easy. But actually, if you want to write it carefully, there were a couple of gaps there that I had missed out on. And in fact, the proof is slightly more tricky than it looks like at first glance. So this one will actually take up the next 20 minutes or something. Right? So let's write. So we proved some basic lemmas, lemma 1 and lemma 2, which I will remind you when the time comes. But basically, the lemma 3 is the main part, one of the main parts of it. Lemma 4 or theorem 4 or something is the big one. So lemma 3. Suppose V is a finite. So V and F are like as above. V is finite dimensional. T is linear from V to V. Suppose lambda 1, lambda 2 to lambda k are the distinct eigenvalues of T. Then there exist integers, positive integers, Ri, such that V is the direct sum of these eigenspaces. Okay. Okay. So now the proof of this is going to be by induction. So let's see. So proof. So let's start now. So proof of this lemma by induction on k bigger equals on the dimension of V itself. N, which is since V is finite dimensional, I can give its dimension the name. Okay, if n equals 0, then it's obvious, so I don't even mention it. Okay, so let's see. So basically, let's just do the base case of n equals 1. N equals 0 is obvious. N equals 1. Maybe I should say this is n equals 0. Okay, so fine. So n equals 1. So what do you do for n equals 1? Second. Yeah, so what happens if n equals 1? Well, then it's one dimensional. Well, actually, every linear map from V to V, where V is one dimensional, is just a map from F to F. And so it is precisely multiplication by a scalar, and that scalar, of course, is the eigenvalue. Right? And E1 is the eigenvector, just the one scalar itself. V is the eigenvector. But the point is, then because T is equal to, then T equals lambda times, let's say lambda 1 times identity for some scalar. Identity 1 cross 1. For some scalar lambda 1 in F. But if T equals that, then you just set R1 equal to 1. And you are done. Right? The vector space is one dimensional, and that is the kernel of this. Yeah. Okay, so now the induction step. So now assume that the result holds for n minus 1, and now of course you assume that n is therefore bigger equals 2 now, and you want to prove it for n. Fine. How do you do so? Okay, so first of all these eigenvalues obviously exist. So first of all, given V, there exists an eigenvalue by the hypothesis. There's at least one of those, lambda 1 of Pt of x. Okay, now what does lemma 2 say? So lemma 2 has said, let me just remember this. Lemma 2 said that if you have n eigenvalue and you define the generalized eigenspace, let me remind you that V prime lambda equals generalized eigenspace. So this is the set of V, let's say lambda 1. V in V such that there exists an m integer with let's T minus lambda 1 identity to the power m of V equals 0. Okay, so not that this T minus lambda 1 identity times M is 0, that will make V an eigenvector, but this power M times V is 0. So that's why it's called the generalized eigenspace, and that is the eigenspace, that is the so this is a subspace, and the point was that if V is finite dimensional like this, then this is actually equal to, lemma 2 said that this is equal to, this equals the kernel of T minus lambda 1 identity to the R1. And so there can be some, there is some integer R1 that works for every single V in this set. Not just that for every V you have some power, no, for all the V's you have the same power R1. That was what lemma 2 said. And moreover, it said that V is the kernel, so V is the kernel of this plus the image of this. V equals this thing, direct sum the image of this thing. Right? That was what lemma 2 had said. And so now we apply lemma 2. So because there exists such an eigenvalue, so we know that we can do this. In fact, maybe I'll just say that. So by lemma 2, okay, so define this. So define this. Define this thing. Then by lemma 2, I'm just literally writing down the statement of this lemma 2, but fine. We'll just say that that's part of the proof. V prime lambda 1 actually equals this thing. And, comma, and V equals V prime lambda 1 direct sum the image of this T minus lambda 1 identity to the R1. So these are what lemma 2 says. Okay. So now we are already sort of good in the sense that, oh, and moreover, this space is also T stable. And now here is the key point. The key point is because that lambda is an eigenvalue, this space is not zero. It contains at least one non-zero eigenvector for lambda 1. In particular, what does that mean? It means that if this is non-zero and this is V, then the dimension of this guy is the difference of dimensions. So it is strictly smaller than dim V, which was N. And we are doing induction steps. So we know that for all smaller dimensional subspaces, this lemma holds. That means that this image, whatever this space is, and I think I will give it a name, I'll probably call it V1 or something. See? Or V prime 1 or something. I'll call it V prime. Yeah. Yeah. Okay, so the two different cases. First of all, it could be that this is the entire space. If this is the entire space, then we are done. Right? Well, we need to say a little more, but then. Okay, so there are two cases now. So let me just say that. So this is why one has to do this carefully, and that's why, as I said, lemma 3 will take some time to do carefully. Okay, so there are two cases. Lemma, yeah, so this is so far so good, and now, yes, lemma 2. So should I call it case 1, case 2? Sure. Case 1. This image, okay, maybe I should give this a name. So let's let V prime be defined to be this image. T minus lambda 1 identity to the R1. So give that the name V prime. So case 1 is V prime is 0. It's literally consisting of the single vector 0. In that case, well, clearly V is equal to this kernel. So that is fine. But we see what was there. We had said that if lambda 1, lambda 2, lambda k are the distinct eigenvalues, then there are positive integers like this. And now I'm saying that, in fact, this summation is only over one term. So I need to prove for you that then, if it is true that this image is 0, then this is the only eigenvalue, and so k is equal to 1 here, and that's why there is only one term. So it's not just obvious here that we are done because V is the direction of one thing. No, because we have to also keep track of the eigenvalues and prove that there are no others. Okay. Then, so we claim that. So now, if lambda prime not equals lambda, sorry, we need to show that. Okay, so remains to show. Then we need to show no lambda prime different from lambda. Sorry, or let's say if lambda prime not equal to lambda, then lambda prime is not an eigenvalue. Okay, so that is what we need to show. Okay, fine. But now what do we know? Well, what do we know? 1 second. What do we know? I just want to see what time it started. Okay. Yeah, so once you know that, then you're done. So let's calculate. Suppose lambda prime was an eigenvalue. So let's see. This is case 2. Case 1. Suppose it was. Yeah, because if not, well, look, maybe I'll just say that explicitly. Indeed, if lambda prime not equal to lambda is an eigenvalue with eigenvector, let's call it V prime. So V prime is the eigenvector for an eigenvalue not lambda. Then let's calculate something like this, right? So let's calculate t minus lambda 1 okay, I'm going to calculate t minus lambda 1 identity, the R1, applied to a scalar alpha v prime. Okay? So, and let me even tell you what alpha is. Then set alpha to be lambda prime minus lambda 1. Sorry, is it lambda? Lambda 1. Lambda 1. To the minus r. Right? Lambda prime is not equal to lambda 1. So this number is a non-zero scalar in the field. So it has a reciprocal, and take the rth power of that reciprocal. And compute now. So t minus this thing times alpha v prime. So of course alpha comes out, everything is linear, and you get t minus lambda 1 identity to be r prime. But t acts by lambda prime, and this acts by lambda 1. And so from a homework problem, this is a polynomial in t, and therefore this is equal to alpha times lambda prime minus lambda to the r1. So this should be r1 here. Yeah, r1 times v prime. But this is exactly the reciprocal of that, so they cancel, and you get v prime. And of course, you know that this v prime eigenvector is not 0 because it's an eigenvector. Okay, so what do we get? This implies that you have a non-zero vector. This non-zero vector v prime is in the image of this map. But we just said that v prime, which was the image of this map, was 0. So that's a contradiction. And what is it a contradiction for? If this is an eigenvalue, sorry, indeed if lambda, this if is a contradiction because we assumed that some other scalar was an eigenvalue, and we saw that the assumption, this assumption is contradicted. So the contradiction, and so we are done. So the lambda 1 is the only eigenvalue. So this is how you, this, as I said, that's why this lemma actually turned out to be trickier than I thought. In that Princeton University website, it's just written, it's obvious. But yeah, once you start writing it down in full detail, you see that there are some subtleties. This was case 1. This cannot happen, basically. Well, this was case 1, in which case k equal to 1, lambda 1 is the only eigenvalue, and we are done. Case 2. Case 2 is when v prime is non-zero. In that case, v is equal to v prime lambda 1 plus something that is strictly smaller dimension. And now therefore the induction hypothesis applies, and you can claim that v prime is the direct sum of those kernels. Okay. But moreover, now the first thing is we have to say that the eigenvalues on B prime are indeed exactly all of lambda 2 through lambda k. Okay. So then my lemma 2. Okay. So then B prime 0 is less than the dimension of B prime. Is strictly less than the dimension of V because the kernel is non-zero, so it has positive dimension. Okay. So the induction hypothesis applies. So my induction hypothesis you can write down V prime. Oh, and V prime is T stable. Since V prime is T stable, so that is again by lemma 2. So V prime is the direct sum of whatever sum over some scalars lambda, which are the eigenvalues of the kernels of T restricted to V prime minus lambda identity. To some R, whatever. Let's call them lambda J or J. Okay? Or let's even call them R prime J. And let's call them lambda prime J. So these are the eigenvalues of this map restricted to V prime. And so you have to subtract those eigenvalues and take them to some corresponding integer power. Of course, I'm going to prove for you that these lambda prime J's are exactly the original eigenvalues of T. They are exactly the lambda. But a priori, we don't know. Okay, so the first claim. So now we have to prove a bunch of things. The first thing is that these lambda prime J's are exactly the lambda 2 through lambda 3. Lambda 1 does not occur. Maybe I'll now call it part A or something. So part A claim. Okay, I will prove later on for you also that we have to observe many different assumptions hold to apply the induction hypothesis. Okay, so I need to prove for you that the polynomial on V prime splits as a product of linear factors. Therefore, the eigenvalues are what they are. Right? So let's maybe I should start with that. So the characteristic polynomial of T restricted to V prime splits as a product of linear factors, which is why the induction hypothesis applies. So even before I actually write this down, I should be really proving this part, right? So when we will do that, we will not use that to prove this. Splits into linear factors. Right? This is easy by lemma 2. Lemma 2 says that this V is a direct sum of this and this, and both of those subspaces are T stable. Right? V prime plus V prime lambda 1, right? By lemma 2, a direct sum. With V prime, I need to start with pen probably. So how does the matrix of this thing look like? So with respect to any ordered basis, so take ordered basis of V prime, another ordered basis of V lambda 1. Maybe I should call this B1 and this B2. And then look at the union of this as B, and then take some ordered basis. Well, then what you can check is that the TBB is literally the matrix T with respect to B prime with the basis B1, B2, I guess. B2, B2. And then here T with respect to, I need to write down, I need more space here. Maybe I should use a black pen for a change. What I see is that T, BB is literally T, B2, B2, T, B1, B1, 0, 0. It is literally this block diagonal matrix because they are T stable. That's not hard to check or to figure out or understand for yourselves. Okay, so because of this now, and you also know, well, so in particular, what do you know? In particular, the characteristic polynomial on all of V, right, or with respect to B or B or whatever, is the characteristic polynomial, is the product of the characteristic polynomials of these two matrices. But this characteristic polynomial is exactly the one for T with respect to V prime. So let's call it T with respect to V. Here it is T with respect to V prime, B2, yeah, of X times the characteristic polynomial T with respect to V prime lambda 1 of X. Okay? And so in particular, you already see that this splits as a product of linear factors. So this, I mean, right, so there, this is a product of polynomials, this is a product of linear factors. So therefore, some of those linear factors go here and the others go here. This uses the fact that the ring of polynomials is a unique factorization domain, which meaning that there is only one prime factorization. So just like any number is a product in a unique way of prime numbers, every polynomial over one variable is a product in a unique way of prime factors, which in this case linear factors are prime, so this must be product of linear factors, and so must this be. I will just write down the technical term here, and for those of you who are interested, you might go and check out Wikipedia or some books. Of course, some of you already know what this is. Okay, so that's the proof of the claim, and as a result, you can apply the induction hypothesis and get this. Okay, but you'll notice that this is the restriction of P to B prime. And what I really want is I want to say this is actually the restriction of P to all of V gives you the same space. Okay, but fine, we'll get there. So that is so the first thing is that this is what it is. The second thing is, look, the characteristic polynomial here is going to be x minus lambda 1 to the R1 basically. And so the claim is that lambda 1 never occurs as an eigenvalue over here. So that is the second claim. Maybe I'll call it B, I guess. Yeah, so B is now, so I want to know what the eigenvalues here are. Well, the answer is these are all x minus lambda 1 to the R1. And these are all the remaining lambdas. So we claim 2. The eigenvalues of T restricted to V prime are precisely lambda 2 to lambda k. Okay, so that's what it is. Remember that we already said that V prime is non-zero. So there is at least one eigenvalue. K is at least 2. Okay, that's what they are. Okay. So okay, fine. This is solution. Yeah. So the point is what is the point? The point is I'm saying the set of these eigenvalues equals the set of these eigenvalues. Maybe I'll just write this as the equality of two sets because then you will see the proof is also helped. Okay. So now, so the first point is this: if I take any eigenvector inside V prime, well, V prime is a subset of V, subspace of V. So it's an eigenvector inside V, and so this eigenvalue of T on V prime is indeed one of the eigenvalues of V. So clearly, yeah. So the inclusion this is obvious because V prime is containing V. It's really this inclusion that we want, right? Meaning that, yeah. So that every one of these guys is indeed an eigenvalue, but that is again by the calculation like this, something like this. Right, so I can again take So suppose suppose lambda 2, so say lambda j vj equals, sorry, tvj. So I should say tvj equals lambda j for the j with at least 2. Bigger equals 2. Just like the calculation on that board, you can say the same thing again. I think you can say then, I want to say that Vj belongs to V prime. And therefore, this lambda j is indeed one of the eigenvalues here. So all of these sit inside here, and so the sets are equal. So why is Vj and V prime? Well, V prime is the image of P minus lambda I1 and T M1. So okay, you just check the same thing again. So Vj equals I should say T minus alpha. So this is T minus lambda 1 identity to the R1 of alpha Vj, where alpha this time is exactly the same scalar, except instead of lambda prime, you would put lambda j minus lambda 1 to the minus R1. Right? So when you put this in here, because this is eigenvalue lambda j, you get lambda j minus lambda 1 to the R1 times the same thing to the minus R1, and that is precisely 1. And so indeed, therefore, this belongs to the image. And so because the eigenvectors here for these guys belong to the image of belong to V prime, therefore the eigenvalues here are indeed eigenvalues of this. So both inclusions are proved and we are done. Okay, these are these small claims. So remember, we want to prove that the entire space V is the direct sum of such things, except that this is V. For now, what we have proved is that indeed the eigenvalues here are exactly lambda 2 through lambda k. So you might as well just say j equals 2 through k. You change that. But the only difference, there's a difference. Everything here is good. Life is wonderful. The only difference is that this is t inside t restricted to v prime. And that's what we want to change. And that is the part that I had told you last time. Yeah, so now we know that, so therefore, because of this board, now by the induction hypothesis, this is true. Okay. So maybe I should have maybe not said it here. I'll say that now. Now I will say from these claims, and because V is T stable, and so these claims are verifying all the assumptions that the eigenvalues are lambda 2 through lambda k, the polynomial fixed is a product of linear factors, the map is T stable, the dimension is small. Maybe here you can write in the next show. Okay, so from these claims, and since V prime is T stable, the induction hypothesis implies exactly what I wrote earlier, right? That the V prime is the direct sum, and now I can literally just write j goes from 2 through k, kernel t restricted to V prime minus lambda j identity leads to the Rj. I can even put R prime j because those R prime j's are whatever they are. But then those are the R prime j's. Actually, no, I'll put them, there exists R2 through Rk that this happens. And now all we need to show is that each of those is exactly the same as this restricted to all of V with the same R2 through Rk. And then we are done. So clear? So we part C, claim 3. V prime is equal to exactly this thing without the prime here. T restricted to all of V. Because that is what we want this part to sit inside the in the formula for V. V is V prime lambda 1 directs of all of these guys. These are just V prime lambda J. The same RJ. Okay? And so this kernel is what we are supposed to be calling V prime lambda J's. V prime lambda J. So once you prove this third claim, then the lemma 3 is proved. But as I said, you see, so it takes a little while to prove lemma 3. And I thought I'd skip over it. It has all these subtleties that you must make sure. Okay. Yeah, so next. Okay, so now why is this true? Fine, so let's do this. This may be a slightly long lecture. I'm just warning you. Because this is not exactly a short. So one implication is obvious. Clearly, if you look at the kernel on T restricted to V prime, you get some vectors in V prime. They are the kernel of T restricted to which inclusion is obvious. Yeah. So if suppose you have a vector V in V prime such that V belongs to this thing, then the vector V is in V also, and therefore V belongs to this kernel. We claim that each of them is yeah. So we claim this thing is the V claim is equal. So proof. This is oh. Proof is that first of all V prime equals this, so the inclusion here is obvious. So conversely, now suppose you have a vector V inside the so conversely we claim for j greater than 1, yeah, that what we claim is that this entire thing here, this summand, is sitting inside V prime, is sitting inside the image of the T minus lambda, T to the restricted on all of V minus lambda 1 identity to the R1. So we claim that kernel T minus lambda J identity the Rj is sitting inside V prime for all j bigger than 1. Okay. So this is sort of the thing that I was telling you last time. So again, if you can show this part, then you would show the claim because when V prime is contained in the sum of these, each of these is contained inside V prime. So the sum is contained inside V prime, and so you have equality. So this would prove it. This would finish it. This would show claim 3. And if you show claim 3, then you would show the lemma. Sorry, claim 3 and hence lemma 3. Okay, so why is this true? Okay, this is where you have to do these things. So, okay. What is V0? I thought we called it V lambda 1. I think this was called V lambda 1, so I should not call it V0. V lambda 1. Okay, so we want to show that this is contained here. So take a vector here that let's give this some name. I think. Let's give this the name V prime lambda J. So that V belongs to V prime lambda J. Meaning this kernel of T minus lambda J identity to the Rj. Okay, that V belongs to this thing. Now you can write this down in the terms of lemma 2. By lemma 2, V equals V lambda 1 direct sum V prime, where V lambda 1 is in V lambda 1, so V prime lambda 1, maybe I'll call it V prime. And this is of course in V prime. This is the kernel of this kind of a map for j equal to 1, and this is the image of the exact same map, right? And what do we want to show? We want to show that everything is contained in V prime, so you must show that this guy must be 0. That's what you have to show. Okay, fine. To show V prime is 0. Need to show. Okay, so how do you show that something is 0? If I apply, let's see, what do I apply for? This is where I'm stuck again. If I apply t minus lambda 1 identity to Java to both sides here, let's see what I look at. This will just become 0. No, this is already there. Okay, fine. Right, so t v prime is in v prime, yes. That's t stable. Now, okay, I think there is some more subtlety to be done here. So remember that both of these are t stable. So in particular, if I look at t minus lambda j identity to the rj and apply to v prime. Well, because this is t stable, therefore no. So it's lambda t minus lambda j identity is t stable, and so this thing is still in v prime. And similarly, t minus lambda j identity to the rj applied to v prime lambda 1 is again, because it is t stable, it's still v prime lambda 1. Okay? But now if you add these two equations up, what do you get? You get t minus lambda 1 identity, lambda j identity, as you see now, t minus lambda j to the rj, applied to v prime plus v prime lambda. But what is that? That is exactly v. Okay? And on the one hand, this is equal to what v was in v prime lambda, it was the kernel of exactly this. So if I apply this map to v, I get 0. And 0 is equal to whatever this is, this guy direct sum this guy, which belongs to v prime, direct sum v prime lambda 1. But how can the 0 vector belong to a direct sum? I think you guys know this. Both the components must be 0. That means this vector is 0 and this vector is 0. Okay. Okay, fine. So okay, so what do we get? We get that both of those must be 0. And we want to show that v prime lambda 1 itself. So what do you remember what we want to show? We want to show that this is contained inside here. Which means if you start with a vector here, it must already be this part. So you want to show that this guy is 0. The goal is to show this guy is 0. What we have shown is that t minus lambda j identity R1 to apply to this is 0. So we have, so t minus lambda j identity to the Rj, sorry, not R1, applied to v prime lambda 1 is 0. And we want to show, we want that this vector itself is 0 because the moment this vector is 0, you get here, look at here. If this vector is 0, that means v equals v prime belongs to v prime. So any vector here is contained in here, therefore the whole subspace is, and we will be done. So we just know this much and we want to show this. Okay, fine. So, okay, and now what do we know? But we also have t minus, what was v prime lambda 1? The defining condition of that space was t minus lambda 1 identity. So the R1 applied to v prime lambda 1 equals 0. So here you have two different polynomials. One of them I will call p of t, killing this vector, and one of them I will call q of t, which also kills this vector. So p of t kills v, q of t kills v. V prime lambda 1 equals 0 equals q of t, v prime lambda 1. Okay, and now that's great because now, and this is where this is the part that I told you last time. Since p and q are co-prime, so there exists, I don't know, a of t and b of t in this f bracket t in the polynomial ring. Sorry, there exists a of x and b of x. Oops. The polynomial ring involves variables such that ap plus ax px plus bx qx equals 1. Now apply that thing to this vector here and we get that v is the identity times v, and that is equal to, by that equation, a of t, p of t, v, v I mean v prime lambda 1, of course, v prime lambda 1, v prime lambda 1, plus b of t, q of t, v prime lambda 1. And we know that pt times v lambda 1 is 0, qv times v lambda 1 is 0, so this is 0 plus 0, and that is precisely 1 big 0. So we started from this vector v prime lambda 1 and we did prove that it is 0. And that's what we wanted to show. So this would prove this claim here that this is always 0. Therefore, v always belongs to v prime. So the entire kernel here sits inside v prime. That proves the claim 3, and therefore it shows. Then all that means is that this here, v, t restricted to v and t restricted to v prime, that gives you the same space. Therefore, claim 3 is proved, and therefore, by the induction hypothesis, lemma 3 is proved. So this lemma 3 turned out to be a big beast. It really took a lot of space. Okay, so that is the end of lemma 3. And also now just to take stock of where we are. We are trying to prove the Jordan Canonical Form theorem, right? So let us take stock of where we are. So we have a finite dimensional vector space V. We have a linear map from V to V called as T, and all the eigenvalues, whose characteristic polynomial splits as a product of linear factors. Let lambda 1, lambda 2, lambda k be the eigenvalues. So to take stock, so taking stock of where we are vis-a-vis the proof of the Jordan Canonical Form theorem. So far, so V equals direct. So we have all the hypotheses of the theorem, and we have now V equals the direct sum of 1 I equals 1 to k Vi. Each Vi is now by lemma 3 the kernel, the generalized eigenspace. So Vi equals V prime lambda I equals the kernel with a fixed power T minus lambda I identity to the Ri. There is some fixed Ri for every. Okay, this is what we have. And on each Vi, as we saw, right, on V1, the only eigenvalue was lambda 1, nothing else, because of the kernel thing. Every other eigenvalue sat inside the image part. Right? I mean, or you can try to prove it yourself. You can remember yourself how you prove it. Just again using the lambda I minus lambda 1 I. The only eigenvalue of T, of course, is lambda I. Okay, great. By the above proof. So, again, it's the same thing. If V in V I it's eigenvalue lambda, then this gives you that T minus lambda I identity to the Ri times V is lambda minus lambda I identity to the Ri times V, and that is 0. But V is not 0, therefore this must be 0, therefore lambda equals lambda. So I'm just writing it down very, very quickly, but yeah, this is the same calculation you have seen like 2 times in the previous part of the proof of lemma 3. Okay, great. So that is so far that is where we are. What else do we know? Fine. Moreover, what do we know? We also know, because each of these subspaces are T stable, so PT should have mentioned this earlier also. And also see PT of X on the full space, just again the same way, you write down the block diagonal matrix for each Vi. So this is the product. I goes from 1 to k. P Vi or T restricted to Vi either way of X, which in particular implies that each of these guys being a factor of this and unique factorization domain property, each of these guys also splits into a product of linear factors. Each P Vi of X also splits into linear factors over the field. Okay. But now since the only eigenvalue is lambda I, we know exactly what this is. P Vi of X equals X minus lambda I to some dimension Di. Okay. Okay, great. And in particular, if we write instead of T, if I now take, define Ni, again the linear map from V to V, to simply be T minus lambda I identity. Okay. Then what does this say? It says that, well, Ni to the power Ri, where is Ri? Ni to the power Ri is identically 0 on Vi, because Vi is the kernel of that. So it gets entirely killed by Ni power R. So Ni is a linear map whose power is identically 0. Such maps are what we call nilpotent. Okay. So, and so of course, so this is this. Of course, this is all eigenvalues. What are the eigenvalues of Ni? They are the eigenvalues of T on Vi minus lambda I. All eigenvalues of Ni are 0. And I can even write down the characteristic polynomial therefore, because it is literally the shift. So P Ni comma Vi of x is literally just x minus 0 to the power di. Di being the dimension of di. Okay. Okay, and as I said, and Ni power Ri is identically 0 on Vi. Okay. The zero linear transformation. So if we can show that, so that there exists an ordered basis, let's call it Bi, I guess, of Vi. So if we can show that every one of these subspaces Vi has an ordered basis, such that what? With respect to which Ni is in Jordan canonical form. And by Jordan canonical form we mean with zeros on the diagonal, because those are the eigenvalues. Ni is in Jordan canonical form. And by Jordan, as I said, it means that you have something like this. Something like this. So this is like a 7x7 example. And I wrote it because I will keep using it again and again. Then, what can you say about T? Well, first of all, as I said, T is just a block diagonal matrix on each Vi. So if every one of the Ni's looks like this, then all the T does is the T on the Vi looks like lambda I, lambda I, lambda I, lambda I is lambda I, maybe some other blocks, maybe the lambda J, lambda J, lambda J, lambda K, but that is exactly a matrix in Jordan canonical form with different eigenvalues. Then the Jordan canonical form theorem follows. Since every single T raised to Vi, T restricted to Vi, is as follows. Since PVI, or with respect to BI, sorry, I should have said T restricted to Vi with respect to BI. T restricted to Vi with respect to the basis would then look like the same thing. It would do lambda, 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 1, 1, 0, 0, 0, 0, lambda, 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 1, 1, 0, and the lambda. Because you just add lambda I times identity everywhere. Lambda times. These are all lambda I, I guess. Anyway, and so for every single vector space Bi, you would have something like this as a block, Jordan representation for T. And so when you put together all those ordered bases Bi, you get a matrix in Jordan canonical form. So basically, it's enough to show you have to study these Ni's and show that if we show that there exists ordered basis for each Ni, where Ni has only eigenvalue 0. The Ni's across all the i's have the same kind of structure because we are subtracting lambda times identity from T. So the Ni's are always having eigenvalue 0. So now we have reduced it from all possible different eigenvalues to one eigenvalue, namely 0. And so we study the Jordan canonical form, we'll study nilpotent matrices with that kind of structure. Okay? And now for nilpotent matrices, the point is the characteristic polynomial is always just x power something. So it automatically splits in any field. So I don't need to assume anything about any field. I just need to prove that for my nilpotent matrix, Jordan canonical form theorem holds, then it holds for every single matrix. So that's what the reduction has been to. Okay, so now let's start by defining nilpotent matrices and doing some stuff. So now let me start again. So this would then hold. So that's why we need to prove. So it's enough to prove this if part. Okay. So for that, I need to first define nilpotent matrices. So let me do that. Yeah. Okay, great. 1 second. Yeah. So this is barely half of my lecture, but let's see. I think it's a little more than half of my lecture. So fine. So now let's start afresh. So definition. Let's say V is a first of all for this I can take any vector space over F. So let's do that. And N belongs to the linear map. N is a linear map from V to V. Okay, great. So now, okay. We say N is nilpotent of order R greater than 0 if N power R is the 0 linear transformation, but this is not N power R minus 1. And of course, the assumption is N power 0 is always the identity map. Okay. And the second is we say N is nilpotent if it is nilpotent of some order. If there exists some integer R bigger than 0 such that N to the R is 0. Okay. That is the definition of a nilpotent map. Example. I had told you about the space of polynomials of degree at most n, degree at most n minus 1. That was the polynomials in the end. On this set of polynomials, n is equal to the derivative map. And I can even tell you to what order, right? If you take x to the n minus 1, then applying this n minus 1 times does not kill it. You get n minus 1 factorial. So it's nilpotent of order n. Okay, that's the example. Okay, fine. So now before I prove lemma 4, so the last, there's a lemma 4, but before lemma 4 is a lemma 3.5. And I just called it 3.5, which was not in that website in Princeton. Okay, so let's say V is finite dimensional. And n is nilpotent. Then the minimal polynomial for n is x to the something. Right? I don't know what it is, but it's x to the r for some r. Okay. So in particular, of course, all the eigenvalues of n are 0. Of course, you can say more than that. So if you knew the Jordan Canonical Form theorem, then from here, if you're writing n in that way, you could say that the characteristic polynomial is exactly also of the same form, x to the dimension. But let's not worry about that. That will follow from lemma 4 and so on. Sorry, from the Jordan Canonical Form theorem. Okay, but now why is this true? I won't even write down the proof. The point is, n is nilpotent, then there is some r such that there is some, let's say, r1 such that n to the r1 is 0. But that means x to the r1 is a polynomial that kills n. So the minimal polynomial divides x to the r1. Well, the only factors of x to the r1 look like this. All of them look like this. And of course, n is nilpotent. So at least you have to say, you can't say because n to the 0 is 1, no matter what transformation I take, therefore that r1 is strictly positive. And then why is the last sentence true? Because, well, I remember the roots of the minimal polynomial are all precisely the eigenvalues. We have proved that. So the only roots of this are 0, so the only eigenvalues of n are 0. Okay, so now we get to lemma 4 and then the main theorem, and yeah, that is the next. So you want to prove that every nilpotent guy looks like this with respect to some basis, the matrix that I just erased, and we will get there. Lemma 4, this is also very easy. Say n is nilpotent of order V of order R. So V not equals 0. The point is, this time I don't want it to be just a 0 vector space, it's finite dimensional. And n from V to V is nilpotent. Of order R. Of course, then one has strict inclusions between a bunch of different subspaces. So 0 is contained in the kernel of n, but strictly contained. Is strictly contained in the kernel of n squared. Dot, strictly contained in the kernel of n to the r minus 1, which is strictly contained in the kernel of n to the r. But what was n to the r? It's nilpotent of order r, so n to the r is identically 0. What is the kernel of the 0 map from V to V? This is all of V. So starting from 0 vector space, going to all of V, you have a chain of strict inclusions. The proof is not hard. The first point is because V is not 0 and n is nilpotent. So one has strict inclusions. Okay. So why is the kernel of n not equal to 0? Okay, first of all, the inclusions are clear, right? All inclusions are clear. Whether they are strict or not is the question. Because 0, n applied to, n applied to 0 is 0. 0 is in the kernel of n. If a vector is killed by n, then it's killed by n squared, because n squared times v is n times nv, but nv is already 0, and so on and so forth. Are clear? To prove strictness, let's call that A. Let's say, okay, so the point is because n is nilpotent of a positive degree, right? It has a kernel. It has a, what do you call it, an eigenvector. Or okay, no, actually, let's do it by conclusion. So why is this inclusion strict? Say kernel n is 0. What happens then? Well, then what happens? Now here is where you use the theory of determinants. You may remember that we had done determinants at some point, and now by now it's been a long time since we saw even Kramer's rule. We're looking at Jordan Canonical Form and this and that. Well, now we go back to determinants. So if kernel n is 0, then what do we know? We first of all know that n is 1 to 1. But we also know that V is finite dimensional. So a one-to-one, this is this thing about the sets, right? If you have a one-to-one map between finite sets of the same size, then it is onto as well. Well, similarly, if this is a one-to-one map from V to V between finite dimensional vector spaces of the same dimension. Therefore, it is onto as well, and therefore it is invertible. This is from class. Invertible because it is a linear isomorphism, and therefore invertible. But if it is invertible, then the determinant of n is non-zero. I can define the determinant of any linear transformation because it's independent of the ordered basis I choose. Okay, but now what happens? On the one hand, let's look at determinant of n power r. N power r is a zero map. So regardless of what basis I choose, I get zero. On the other hand, the determinant is multiplicative. So this is the determinant of n power r. And I know that this number is non-zero. Therefore, its rth power is non-zero. So I get a contradiction. I get something starting from zero, I get a non-zero number. This cannot happen. Therefore, this is a contradiction. So 0 is contained in, but strictly contained in the kernel. That is the first one. Okay, that is the first. And the rest of them are going to follow cleanly. The point is, you see, this inequality holds because that's the definition of order. Right? It's the smallest integer r for which this is the all of v. So that means this is not all of v because this r minus 1 is smaller. So this kernel cannot be all of v, therefore there is at least a vector there. Okay. The last inclusion is strict by definition of order by choice of r. So this is part B, part C. The final inclusion is strict. By choice of R. Thus, there exists some vector V belongs to V minus the kernel of n to the r minus 1. Right? So that means n to the r minus 1 times V is non-zero, but of course n to the r kills all of the vector space, so it also kills V. But now what I do is the following. Now let's call it Vi to be n to the I minus 1 applied to V. Let's just choose it. So for every single I apply n so many times to V. Okay. Do I want I minus 1 or R? I think I want R minus I actually. Let's look at n to the I minus 1 of Vi. If n to the I minus 1 of Vi is n to the R minus I plus I minus, it's n to the R minus 1 of V. N to the R minus 1 of V is not 0. Therefore, this is equal to n to the r minus 1 of V. This is not 0. On the other hand, what about n to the I applied to V? N to the I applied to n to the r minus I applied to good God. This is Vi. Then this is n to the r applied to V, which is of course n to the r is 0. So this is 0. Therefore, you have a vector Vi which is in the kernel of n to the I, but not in the kernel of the smaller power. And that proves that every single inclusion is straight. N to the I. Okay, so that proves the strictness of this thing. That's lemma 4. And now with this lemma 4, we can finally come to the end of the lines. We will prove the final result. And this is what I'm going to call the theorem. But before that, I need to make a definition, right? So there's now we have now everything ready. So I don't even need the results from last class. That lemma 2 was, I think, only needed for proving lemma 3. I believe, but we will see. Yeah, but now we are basically ready to prove the theorem, the Jordan Canonical Form theorem, for which, as I said, it's now enough by lemma 3 and so on. We have understood that it is enough to prove the Jordan Canonical Form theorem for one nilpotent map acting on any finite dimensional vector space, and that's what we're going to do. Okay, so now for that, we finally, before we use that theorem, before we prove that theorem, we need a definition. Okay, and then we'll write down the theorem very precisely. Suppose W contained in V are F vector spaces. Okay. We say V1 vectors V1, V2, Vk in V are linearly independent of W. Basically, if essentially what we are saying is if the cosets V1 plus W and so on, the equivalence classes, if you will, these are elements of the quotient space V mod W. And so these are linearly independent in V mod W. In other words, and this is the definition I gave you, fine. In other words, if you have summation Ci, Vi, I goes from 1 to k, belongs to W, then all Ci equal to 0. Okay. So for example, if my subspace W was the trivial zero vector space, then this linear independent of 0 is exactly the same as linear independence, because it's saying if summation Ci Vi equals 0, then all the Ci are 0. That's just the usual linear independence. So example, W equals 0 V implies this is simply usual linear independence. Yes. If W is a zero space. Let me say that. Okay, so now we can write down the theorem. And so this is literally Jordan Canonical Form theorem for nilpotent maps. And I will illustrate this theorem with an example, with that same 7 cross 7 example. Let's start it. Now the final theorem then. That's what this theorem really is. Why not? Let's specify the degree as well. Okay, there are two parts to it. So given a set, this is the real part to be proved, and the second part is the corollary that says the Jordan Canonical Form theorem is proved. Given a set S of B, of vectors linearly independent of W, sorry, what is W? There is no W here. Of the degrees are here, so the W is the kernel of n to the r minus 1. Okay, given such a set, one can find a finite set. There exists a finite set think it's called alpha 1 through alpha m. So, which contains this set B containing alpha 1, alpha m, which contains S, such that the non-zero elements among these elements alphas, then the nilpotent maps apply to the alphas, then the square of the nilpotents apply to the alphas, and so on. And J alpha I, 1 less equals I less equals M, and then J is bigger equals 0. So n to the 0 alpha I is just alpha I. Form a basis of B. And the point is, you take this basis in some suitable ordered way. That, with respect to that, the nilpotent map is going to be Jordan. Okay, so the second part now says that. Basically, it says that BI. So let's call this so let's call this set BI. This set, and of course, as I said, we want to take the non-zero elements among them. So we remove the 0. And V equals span of BI. So BI is this, there's some ordering of the BI that we will care about. So BI equals span of BI. Okay, great. Now what do we do? Oh, but the point is here, I'm only going to I'm fixing my I. That's the whole point. So only the J varies. That is the big mistake I've been making. Right? So the point is, there is no fixed I here. But now I'm going to say fix alpha I. Just look at alpha I squared, and so on. Alpha I, n square alpha I, and remove from it the 0 vector. Now we are cooking. And it defines that Vi with the span of this. Then this is an ordered basis. So oops, I should really I mean this in the ordered sense, if you will, right? So you start, the first element is alpha I, the second is n alpha I, and you keep going until the point where you hit a 0. Then you stop. Those are non-zero elements. The claim is they are linearly independent. In fact, they form, right? Together they form a basis. So just take the same I and vary all the J. That forms a linearly independent set. And then it forms, of course, the basis of its span. Then with respect to this Bi, if you restrict n to this vector space I and take the matrix with respect to Bi, then you can check, you get the Jordan block of size whatever, mi, 0. Sorry, mi, 0 eigenvalue, which is just 0, 0, 0, 1, 1, 1, the rest of 0, 0. That is the thing. And of course, and we have already seen this part, V is the direct sum of the Vi, because that's what the basis does to the coproducts. Right? I goes from 1 to n. The coproduct of the basis is the basis of the coproduct. So that's really what the theorem is saying. And the moment you have this is exactly the Jordan Canonical Form theorem. You have a bunch of different Jordan blocks. That's all you want to show. So this part, therefore, this part too finishes the proof of the Jordan Canonical Form theorem. And this is straightforward from part 1. You have to work out that once you have these things, then the way the matrix acts on the span of these guys is exactly by this matrix. But that is a verification that I will leave to you guys to check. Because I'm telling you the action with respect to that basis. So it's literally writing out what the basis looks, how the matrix looks like. Okay. So proof. So finally, let's get down to the proof of this. And yeah, we still have 10 more minutes, but I will probably take 20. Sorry. So proof. So first of all, 2 follows from 1. And I will leave it to you guys to check. This is literally just a check about that this is the matrix. and that automatically implies the Jordan Canonical Form theorem. The general Jordan Canonical Form theorem, not just the one for nilpotent elements. So for 1 now, the proof is by induction on the nilpotence degree. Okay, so yeah. If R equals 1, if R equals 1, then the n to the 1 is 0. And n to the 0 is identity. So n to the 1 is 0. But that means n is the 0 map. If n is the 0 map, then well, with respect to any basis, you get a Jordan block because you just get zeros. So yeah, that's trivial. The base case. And sorry, R equals 1, n equals 0, and this is trivial. So now we just need to do the induction step. Okay, so let me first erase. I will need this definition. I will crucially need to use this, okay? And obviously, we wrote down the definition just to prove this theorem. Okay, so this is the last step. Of course, as I said last time, R is bigger equals 2. Now, so we had this lemma 4, right? That was that there exists, so one second, I need some water. Okay, I also want to do a, how do I do this? I want to do a in parallel example. So I'll use a black pen for my example. Okay, and then I will. So what was lemma 4? Lemma 4 said that these inclusions are strict. That's right. Because these inclusions are strict, given a set of vectors linearly independent of this kernel, right? So the point is this kernel is not all of V. So by choice of the degree, I can find at least one vector in V that is not here. And that vector forms a singleton set of vectors linearly independent of this thing. Right? So not by lemma 4, but by choice of degree. The point is, if this set is empty, you may as well add an element to it, which is not in this kernel, but is in V. So by choice of this R, you can always assume that S is non-empty. W without W, L, O, G. This stands for without loss of generality. S is non-empty. Okay? But that means, well, if that means there is at least one non-empty set, which are vectors independent of that. So you can extend it to a finite non-empty set, and in fact, a maximum possible one. Because of course those vectors must be linearly independent themselves, and they must therefore be at the most dimension of V many. Okay. So can I extend? First of all, A. Now I'm going to go and break it up into parts. So the steps to choose S contained in S1, and I will call S1 as alpha 1, alpha m prime. So fewer many. Okay. Linearly independent of linearly independent of this kernel. N to the R minus 1 of maximal size. And that means any set of size at least m prime plus 1 many elements cannot be linearly independent of this space. That's the maximal size part. Okay, so basically, for example, I'm going to again remind you of this matrix that we looked at. 0, 0, 0, 0, 0, 0, 0. The 7 by 7. Right? And of course, everything gets a 0. Okay. Now I'm going to tell you what my S1, S2, S3 are. So here S1 is E3, E6. Why is it this way? Okay, let's do some examples. Okay, so let's see. So let me write some stuff down. So kernel of n, this is my matrix n. I'll write down the proof there. I'm going to write down the examples. Kernel of n is span of E. Let's see. If I multiply by E3, I get the. If I multiply E1, I think E1 is there, right? Span of E1, E4, E7. You can check. If you multiply by those things, well, you can check. Kernel of n square. I will add some more elements. I will have to add E1, E2, E4, E2, E4, E5, E7. Okay? And n cube is 0. So kernel of n cube is just identity, is the whole vector space. Okay? But now what I'm going to say is now I'm going to tell you what are my S1 spaces. S1 has better be independent of the kernel of n square. This is a 7-dimensional space, out of which 5 are in the kernel of n square. So I'm just going to take the remaining guys, E3 and E6. Okay? And now I'm going to expand it into into S2, which is, what is it? But it is independent of these guys, so that means I can further add E2, E3, E5, E6. And then there's S3, which is independent of kernel of N3. But N3 is 0. So it's just independent. It's the full basis. And so the full basis is the standard basis. So S3 equals the standard basis. So this is what I'm going to do in the general case, in blue ink on the next board. Okay. The point is that every step we keep expanding. So at every step you see we get some more elements. So what elements do we get? We started with these 3 elements. We started with these 2 elements. They are linearly independent of this thing. Then you see here, if you apply this matrix n to E3, you get E2. If you apply this E6 n to E6, you get E5. So I didn't get anything more. But then here I got one more element, which is E7. So those 2 elements plus E7. Those are my alpha 1, alpha 2, alpha m, which is alpha 1, alpha 2, alpha 3. So E3, E6, E7. Here m is equal to 3. So m is equal to 3 here. And this is my alpha 1, this is my alpha 2, and this is my alpha 3. And now the point is that the basis, so look at the basis of n, the powers of n applied to alpha 3, it's just E7 and nothing more because n times E7 is 0. So E7 forms one Jordan block basis. Similarly here E3, look at E3, then apply n once, you get E2, apply n once more, you get E1. So maybe I should write this down. And those 3, E3, E2, E1 form another block. E7 and then n E7 equals 0. So you must not, you can never include 0. The non-zero elements among these guys forms a Jordan block. Not forms a Jordan block. Take the span of E7, you get V whatever. V equals FE7. And then if you look at P on V cross P, this is a Jordan block. With respect to the basis with E7. This is the basis B. Okay. This is, I'll call it B3 because it's the third block. And this is the Jordan block, which is the 0 block. Similarly, if you look at E3 and then n E3, which is E2, and then n square E2, E3, which is E1, and you call this as the basis B, B1, let's say, then again you get this Jordan block. Okay. And similarly for the third one, E6, n times E6 is E5, n times E5 is E4. Take the span of those, look at the basis with respect to that, and you get the second Jordan law. And so that's exactly what this theorem is saying in an example. And these spans that I added up, those are what I will now write down in the general. Is this part, so I need space to write stuff. So we'll finish this proof in general and then we will stop. But yeah, that's why this is probably, no, this is certainly the hardest result in the entire course. So back to the proof. Okay, so choose this thing of maximum size. That was part A. The part B, first of all, is the moment you have this alpha 1 through alpha n prime linearly independent of that kernel, if you look at n alpha 1, I'll apply that nilpotent map, n alpha n prime. So meaning here, instead of E3 and E6, if you look at E2 and E5, they are linearly independent of a smaller power. One smaller power, n to the r minus 2. Okay, yeah, so we are just about past time, so but I'll need a little more time, 10 minutes or so, maybe 15, hopefully not 15, we'll see. Okay, and then the proof is easy. Suppose summation Ci n alpha I now belongs to kernel n to the r minus 2. Then that means that applying n to the r minus 2 to this becomes 0. But that means if I take the n out, then applying n to the r minus 1 to the summation Ci alpha I gives you 0. But that means that all Ci are 0. By choice, by definition. Okay, so that is part B. So now, let V prime be the kernel of n to the r minus 2, r minus 1. So remember, our induction was on the degree. Now this is clearly, so n has a smaller nilpotence degree of V prime. Therefore, you can write down the Jordan basis of V prime. But also, remember that by lemma 4, and this is another key part, this is strictly contained here. Therefore, it has smaller dimension as well. Because it's smaller dimension, it has smaller nilpotence degree, and so you can continue. Okay. So by induction hypothesis, there exists a Jordan basis or whatever. Or more precisely, remember now, so look, the previous original set was this set of linear independent of this of maximum size. From that you obtained that this n alpha 1 prime to n alpha n prime are linear independent of this guy. And that is exactly the assumption of part 1 of the theorem. So by induction hypothesis, you can extend this set to a bigger one. Should I give this set a name like S prime or something? What is S prime? No, that is not S prime. So n alpha 1, n alpha n prime extends to a larger set satisfying those assumptions to a set let's just say satisfying part 1. Of the theorem, right? So all those things are satisfied. But of course, it has satisfied part 1, not in the full space V, but in the space V prime. I should give this a definition. Fine. Let's give it a name. So let's say, and now you will see why the choices were made. N alpha 1, n alpha n prime, and the remaining ones I'm going to call alpha m plus 1, alpha m plus 2, and so on. M prime plus 1, alpha m prime plus 2, alpha m. Okay, so basically what we are saying over here is I would say look at look at the kernel of n to the r minus 1. So look at the kernel of n square. On this 5-dimensional space, instead of looking at E3 and E6, I look at E2, I look at E5, that is n alpha 1 and n alpha 2. These are the alpha 1 and alpha 2, n alpha 1 and alpha 2. And I extend to this alpha 3. This is n alpha 1, n alpha 2, and this is alpha 3. This is my extra element that I get, such that these guys, these three guys, and their powers, n apply to them, meaning E1 for this one and E4 for this one. Form a basis, form a Jordan Canonical basis of the nilpotent transformation on V prime, on the span of these guys, not on the full 7-dimensional vector space. Okay, so that's what we're saying. And now the claim obviously is that alpha 1 through alpha m, not the n's, but these, remove the n's here, these alpha 1 through alpha m prime and the rest of them is alpha m. This is the desired set for property 1. We know that we could produce such a set for the smaller dimensional vector space by the induction hypothesis, because it has a smaller nilpotence degree as well. But now we will say that in fact removing these n's here gives you the correct desired space for the whole set for the whole space. And once you prove that, you're done. That's the induction hypothesis. So part 1 is proved, and as I said, part 2 follows from it, and therefore claim alpha 1 to alpha m prime, and then again alpha m prime plus 1, alpha m. What am I doing? I can't draw square brackets today. It's a bad day. Is the desired set in V. Not in V prime, that was this set, but in V itself. Okay. So, proof, and that's finally, as I said, the proof. So first of all, what we already know is from, let's give this a name. Okay, let's call this, not this. This is not S prime. So first of all, let S prime be n alpha 1. Sorry. So I take these guys, n alpha 1, n alpha n prime, and then I apply the powers of j. So n to the j alpha 1, but there was already an extra n, so j plus 1 here. And then n to the j alpha n prime plus 1, n to the j alpha m. So first of all, they define S to be the set of all these things and the powers of n applied to them. Then S minus 0 is the basis of V prime, that we know by the induction hypothesis. S prime minus 0 is the basis of V prime. Okay, so that we know just because of the choice of the S prime. And what was V prime? V prime is kernel n to the r minus 1. So we just need to show that adding just these extra n prime many elements, alpha 1 through alpha n prime, added to these guys, gives you a basis of V. That's all. That's all that needs to be shown. Right? So need to show. I'm just telling this is, I don't need to say it, but I really want to write things out and spell it in detail. S prime union alpha 1 alpha m prime minus 0 is a basis of V. Meaning to these 5 elements, sorry, yeah, I add my original alpha 1 and alpha 2, E3 and E6, and I get my standard basis, which is a basis of V, with respect to which my matrix is in Jordan Canonical Form. But that was part 2, so that follows. I just need to show it's a basis of V. Once I do that, I prove part 1 and part 2 follows, and that's where the Jordan Canonical Form shows up. How do you show it's a basis? Well, you know the same. You know the drill, you show it's linearly independent, and you show it's spanning. And that's the end of the so linearly independent. So suppose summation this thing is 0. Say summation, should I say Cij? No, I'm going to do it more cleverly. Suppose Ci alpha I goes only from 1 to n prime, not to the full m. Plus summation, S prime is a set, right? So let's say S prime, let's say S belongs to S prime minus 0. And I'm going to index my set with this. So DSS. So it's a linear combination of these elements, these are the coefficients, and of these elements only to the m prime, not the full thing. And the coefficients are Ci. Suppose this is equal to 0. Okay. But now what do we know? Okay, first of all, this means that summation Ci alpha I equals summation minus ds is normal s and s belongs to this same set s prime minus 0, and this I goes from 1 to n prime. But now what do we know about the original alpha i's? Those were linearly independent of, so there was a maximal set linearly independent of the kernel of n to the r minus 1. And all of this is in v prime, which is kernel of n to the r minus 1. And these guys were linearly independent of that set. So how can it be that a linear combination of these guys is in this space? The only way by definition is all Ci are 0. So first of all, if we had this linear combination, we proved that the first coefficients are all 0. But what does that mean? It means that now this linear combination is 0. But this is a linearly independent set. It's a basis. We know it's a basis. Right? This S prime here is a basis. How can linear combination of a basis be 0? All those coefficients are 0. And so, we are done. That proves that that set that we desire, the original set minus 0, together with the original elements alpha 1 through alpha m prime, is already linearly independent. Now the only remaining claim is that it spans all of V, which is the kernel of n to the r, as opposed to kernel of n to the r minus 1. Okay, that's like 2 lines. Okay, so let's start. So let's assume a contradiction. Say alpha naught belongs to V minus the span of S prime union whatever these things minus 0. Okay, suppose alpha naught belongs to this. Great. Then the claim is that if I look at alpha naught, there's a reason why I call it alpha naught, of course. If I look at alpha naught and the original n prime many elements, then this is linearly independent of V prime. And why is that a problem? Because this n prime was said to be the maximum number of such vectors which are linearly independent of V. Now I am producing m prime plus 1 many elements. What's going on? How can that happen? Right? So that would be a contradiction that would prove the theorem. This would contradict the maximum. This would contradict the maximality m prime. So therefore a contradiction that would prove that such an alpha naught cannot exist, and therefore we are done. Proving the theorem. Or finishing the proof. Okay. So how do you show this is linearly independent? So proof of the theorem. And that is the final part of this theorem and hence of the Jordan Canonical theorem. Okay, so say C naught alpha naught. I mean, I could have written this as I equals 0 to n prime, but I want to keep them separate so that, yeah. Suppose the linear combination is 0. Sorry. A linear combination isn't V prime. You want to show that all the CIs are in fact 0, including C naught. Well, the point is the following. Okay? Oh, sorry, and not all CIs are 0. Right, we want to prove that this happens. Assuming that alpha naught belongs to V minus that span, we want to prove this happens for whenever alpha naught is such an element. Suppose this doesn't happen, that means that you can find a linear combination which is non-trivial, which is non-trivial and is in V prime. Right? Because otherwise, if you could never find it, then you're done. So suppose so suppose you have this thing. Now, if this was 0, actually maybe I don't really need to say that, right? I want to prove that all the CIs are 0. Suppose this was 0, then all of them would have to be 0. Okay, so if CI is 0, then wait. If C naught is 0, because we already know that these guys are linearly independent of V prime, so therefore all CIs are 0. If C naught is non-zero, then what can you do? There are two cases, right? If C naught is non-zero, then I guess you can write down then what do you know? Then C naught alpha naught is a linear combination of something in V prime and these guys. Right? So all of those guys basically. Yeah, okay. And that for some reason, I'll leave it to you guys to check why. S prime union alpha 1 to alpha m prime. Okay, right? So there are two cases, as I said. So suppose if C naught is non-zero, then this is what it is. So we need to show just that this is the basis. Let's just take a step back. Okay? So we started with an induction. So yeah, we started with something. We looked at the n alpha 1 to n alpha n prime. We extended that set with the n's to something on V prime. And now we are saying that add these guys and remove the n alpha 1s because those already lie in the powers here. And so then you're done. That is the required set in V, whose integer powers of n's together with this set minus the 0 element forms the basis. Right? So, and what we said was already we know something is the basis of V prime here. The S prime minus 0 is the basis of V prime. We want to show that adding these extra elements, the original, the ancestors of the n alpha 1 and n alpha n prime, gives you a basis of V. First, we proved it's a spanning set, a linearly independent set. And for spanning set, we said suppose there is a vector not in the span. Okay? The claim is that then that vector together with these guys is linearly independent of the kernel of n power r minus 1, which would contradict the maximality. Okay, so how do you prove such a statement? Suppose you take something like this and it's in V prime. You want to prove that all of those guys must be 0. Fine. So if the original first coefficient is 0, then all of them are 0. If the first coefficient is not 0, then look at this vector itself, right? So this is, look at this. This is Yeah, alpha naught is in V minus this. So alpha naught cannot be 0 because 0 is in the span here. So alpha naught is a non-zero vector. This is a non-zero scalar. Their product is a non-zero vector. Right? This non-zero vector is in the span of what? It is equal to something in V prime minus summation Ci alpha. So it's in the span of this or this and this. Right? So it's, and what can you say about that? The claim is just that the C naught must be 0, and that's a contradiction basically. So why is that true? And that would be the end of the lecture, so I should really stop here. But anyway, so maybe I'll leave it to you guys to figure out why, because I'm too tired right now to do something. But yes, apparently the point is this already implies this. I wrote it in my notes without any proof. So I'll leave it to you guys at the very end, because I think I've justified everything else in this proof today. But I will leave it to you guys to figure out why C naught equals 0 from that last statement. Given whatever happens on this board already. Yeah. So yeah, okay. So that's obvious, right? What is the alpha naught? What is the choice of alpha naught? Alpha naught is a vector not in the span of this. But C naught times alpha naught is in the span of this. How can this be my choice of alpha naught? Actually, okay, this proof should be simplified. That's the whole point. I wrote a horrible proof. There's not two different cases. Suppose I have a linear combination like this. Implies C naught alpha naught, which is as simple as that, belongs to the span of V. But V prime is the span of S prime. So S prime union alpha 1 through alpha M prime minus 0. Okay, C naught alpha naught belongs to this. And we know that alpha naught does not belong to this. That's exactly what we're saying here. So how can it be that a vector doesn't belong to this span, to this subspace, but a scalar multiple of that vector belongs to subspace? Okay? The subspace is closed under taking non-zero multiples. So if this C naught was non-zero, then I could multiply by C naught inverse and get that alpha naught belongs here. That's a problem. The only scalar C naught such that C naught alpha naught belongs to a span and alpha naught doesn't is the C2 scalar. Sorry. And since now C naught equals 0, therefore this linear combination is in V prime. But now because these guys were linearly independent of V prime, therefore all the other Ci's are 0. And that was what we wanted to do. Okay, so finally I'm done, and yeah, almost 1 hour 30 minutes. I'm very sorry. But yeah, this was a long proof. The original lemma 3 was the villain. I thought it was obvious, but that took up a lot of the time. And even these guys developing it carefully took some time. But yeah, now the Jordan Canonical Form theorem is finally proved. And that's the end of this class, this lecture. So next time we will start with, I guess, bilinear forms and symmetric bilinear forms, followed by inner product spaces. Okay, that's it for today.